Watch this small instrumented sphere glide through a fluid chamber. A strobe marks its position once every second. The marks keep moving forward, but each step is shorter than the one before it. Nothing removes the same amount of speed each second. Instead, the slowdown itself fades as the sphere slows. What rule produces motion like this? For this film, we deliberately enter the linear drag regime. A smooth, non-rotating sphere moving slowly enough that the drag force is proportional to its velocity. Our question is no longer merely why does it slow? It is, what exact story does linear drag write into its motion? Begin with horizontal motion. Take x to the right and let the surrounding fluid be still. The sphere moves right, so linear drag points left. Its vector law is Fd equals minus bv. The coefficient b is positive, and the minus sign carries the direction. Drag opposes the velocity relative to the fluid. Gravity still acts downward, but it has no horizontal component. So the horizontal equation closes on itself. M times dvx by dt equals minus bvx. This uncoupling is a special gift of linear drag. Each component of minus bv is simply minus b times that component. Later, x and y can be solved separately before they are recombined. Now look at the feedback hidden in that equation. When the sphere is fast, the backward force is large, so its speed falls rapidly. When the sphere is slow, the force is small, so its speed falls gently. The force weakens in exact proportion to the speed it is trying to erase. Divide by m and define tau, the response time, as m over b. Then dvx by dt equals minus vx over tau. Separate the changing speed from time, dvx over vx equals minus dt over tau. Integrating says the logarithm of speed falls steadily. Therefore, the speed itself falls exponentially. Vx of t equals vx0 times e to the minus t over tau. The curve is smooth because the cause is continuously weakening. Tau is not decoration, it is the clock of the system. After 1 tau, only e to the minus 1, about 37% of the initial horizontal speed remains. After another tau, 37% of that remainder survives. Linear drag removes the same fraction in each equal response time interval, not the same number of meters per second. The formula tau equals m over b also predicts how the object will respond. More mass means more inertia and a longer memory of the initial speed. A larger drag coefficient means stronger resistance and a shorter memory. On the graph, changing vx0 stretches the curve vertically. Changing tau stretches it horizontally. Tau tells us how long the sphere remembers how it started. Velocity tells us how quickly position accumulates. Integrate the exponential speed from 0 to t. The result is x of t equals x0 plus vx0 tau times 1 minus e to the minus t over tau. Watch what that means physically. Early time intervals add long pieces of distance. Later intervals add shorter pieces. The infinite stack of shrinking pieces has a finite sum. As t grows, the exponential disappears, and x approaches x0 plus vx0 tau. If x0 is 0, the limiting distance is vx0 tau. The sphere does not strike an invisible wall, and the mathematics does not abruptly stop it. It keeps creeping forward while its remaining speed and remaining distance both shrink exponentially. Linear drag turns an endless approach in time into a finite horizontal destination. Keep the same sphere and the same fluid, but rotate the laboratory into a vertical shaft. We choose y positive downward, the direction of gravity. This choice makes g positive. When the sphere falls downward, gravity contributes plus mg, while drag points upward and contributes minus bvy. Newton's second law becomes m times dvy by dt equals mg minus bvy. Notice what changed. Horizontally, the target speed was 0 because drag was the only force in that direction. Vertically, gravity keeps supplying a constant downward pull. Drag will grow until it can balance that pull. The motion now has a non-zero target. Release the sphere from rest. At first, drag is 0, so gravity gives nearly g downward acceleration. As speed grows, the upward drag arrow grows. That reduces the net force and the acceleration. Eventually, the two force arrows match. mg equals bv terminal. At that balance, acceleration is 0 and the speed stops changing. Solving the balance gives v terminal equals mg over b, which is also g tau. Terminal velocity is not a mysterious maximum imposed on motion. It is the velocity at which the constant force of gravity and the speed-dependent drag cancel. The sphere approaches it smoothly. In the ideal exponential model, it does not need to arrive at it at one special finite instant. Here is the unifying move. Do not track Vy by itself. Track its gap from the target. Define u equals Vy minus v terminal. Because v terminal is constant, u obeys du by dt equals minus u over tau, exactly the horizontal decay equation. So u of t equals u naught e to the minus t over tau. Restoring Vy gives Vy of t equals v terminal plus the initial gap, Vy naught minus v terminal, times e to the minus t over tau. This one formula contains 3 stories. Start below terminal speed, and the sphere accelerates downward toward it. Start exactly at terminal speed, and nothing changes. Throw it downward faster than terminal speed, and drag exceeds weight, so it slows down toward the same target. Terminal velocity attracts motion from either side. For drop from rest, Vy naught is 0. The general solution becomes Vy equals v terminal times 1 minus e to the minus t over tau. The graph climbs quickly, then bends toward a horizontal asymptote. After 1 tau, the sphere has reached about 63% of terminal speed. After 2 tau, about 86%. After 3, about 95%. Those numbers are not separate facts to memorize. Each tau leaves only 37% of the previous velocity gap. The acceleration tells the same story. It begins at g and fades like ge to the minus t over tau. The object keeps speeding up, but by a smaller amount each moment because the growing drag continually cancels more of its weight. Integrate the vertical velocity once more. With downward positive y, the position is y naught plus v terminal t, plus the initial velocity minus v terminal, times tau, times 1 minus e to the minus t over tau. For drop from rest, this simplifies to y minus y naught equals v terminal times t, minus tau times 1 minus e to the minus t over tau. The curve begins with a familiar rounded shape of acceleration from rest. Much later, the exponential correction is almost constant, so equal time intervals add almost equal distances. On a position versus time graph, the curve settles toward a straight line whose slope is v terminal. The transient remembers the release, the long time line remembers the force balance. Taylor examples show how dramatically the time scale can change. A tiny oil drop like those in the Millikan experiment can have terminal speed about 6.1 times 10 to the minus 5 meters per second, and tau about 6.2 microseconds. It adapts to its terminal speed almost immediately on a human clock. A larger mist droplet can have terminal speed around 1.3 meters per second, and tau around 0.13 seconds. Same equations, very different motion. Mass, size, medium, and drag coefficient set both the target speed and how quickly it is approached. Linear drag is most useful here because these small, slow objects live in the viscous regime. Horizontal and vertical motion now share one idea. A velocity component exponentially forgets its initial value and approaches the velocity selected by the forces. Horizontally, the target is 0. Vertically, with downward positive y, the target is v terminal. In compact form, dv by dt equals minus v target over tau. We have solved the two components, but we have not yet combined them into a projectile path or calculated a range. That is the next step. In the next lesson, the horizontal decay and vertical approach will meet on one moving projectile, and the trajectory itself will reveal what linear air resistance changes.